15th of March, 1943. Mid-Atlantic, 700 miles from Liverpool. Captain Ernest Whitmore stands on the bridge of the Liberty ship SS John Harrison as black smoke rises from the forward hold. Below deck, flour dust has ignited. The explosion killed 3 crewmen and destroyed 8,000 tons of grain bound for Britain. Whitmore is a Royal Navy technical officer assigned to investigate cargo losses. This is the 9th grain ship to burn in 4 months. Whitmore descends into the damaged hold wearing a respirator. The air is thick with suspended particles. He runs his gloved hand along the bulkhead and feels the heat still radiating from the steel. The flour had been loaded in Baltimore 2 weeks earlier. Standard procedure, standard ventilation. Yet the hold became a bomb. He examines the ignition point near the engine room bulkhead. Scorch marks radiate outward in a pattern he has seen before. The flour dust formed a cloud. A single spark from static electricity was enough. The confined space amplified the blast. He collects samples of the residue and photographs the damage. The evidence is clear. Fine particles suspended in air become explosive when concentrated. Back in London, Whitmore reports to the Ministry of War Transport. Britain is starving. German U-boats sink 40 ships per month. Every lost grain carrier means tighter rations. The ministry cannot afford to lose vessels to internal explosions. They give Whitmore authority to solve the problem. He has access to merchant fleet records and engineering resources. His orders are simple: stop the explosions. Whitmore begins with data. He reviews loss reports from 1942 and early 1943. 17 Liberty ships carrying grain have suffered spontaneous explosions. 12 were total losses. The pattern is consistent. Explosions occur in holds with poor air circulation. They happen during Atlantic crossings when ships pitch in rough seas. The motion stirs settled flour into clouds. Engine heat and static discharge provide ignition. He visits the Port of London and inspects grain loading operations. Longshoremen pour flour into holds through chutes. The process creates massive dust clouds. Whitmore watches particles settle on every surface. He touches a metal railing and feels the static charge. In the confined space below deck, these conditions are lethal. Whitmore consults with industrial safety engineers who work in grain elevators. They explain the mechanics of dust explosions. Particles must be small enough to remain airborne. The concentration must reach a critical threshold. An ignition source must be present. All 3 conditions exist in Liberty ship cargo holds. The engineers show him prevention methods used on land. Ventilation systems that keep dust concentrations low. Grounding cables that eliminate static buildup. Humidity control that weighs down particles. He adapts these methods for maritime use. The solution requires 3 integrated systems. First, forced air circulation to prevent dust accumulation. Second, grounded metal baffles to dissipate static electricity. Third, humidity control to keep particles from becoming airborne. Each system must function in salt air and rough seas. Each must be simple enough for merchant crews to operate. Whitmore designs the ventilation system first. He specifies electric blowers mounted in each cargo hold. The blowers draw fresh air from deck level and exhaust it through vents near the keel. The continuous airflow prevents dust clouds from forming. He calculates the required air exchange rate based on hold volume and typical flour cargo density. The system must cycle the entire hold atmosphere every 40 minutes. The grounding system is simpler. Whitmore orders copper cables installed along bulkheads and deck beams. The cables connect to the ship's hull, creating a path for static discharge. He adds grounding straps to loading equipment and requires crew to wear conductive footwear. Every metal surface in the hold becomes part of a unified electrical ground. Humidity control presents the greatest challenge. Ships cannot carry large water supplies for misting systems. Whitmore develops a passive solution using seawater-cooled condensers. The devices lower air temperature in the holds, causing moisture to condense. The increased humidity makes flour particles heavier and less likely to remain suspended. The system requires no pumps or external water source. By May 1943, Whitmore has working prototypes. He selects the SS Thomas Jefferson for the first installation. The ship is in Liverpool for repairs after a U-boat attack. Whitmore supervises the retrofit personally. Workers install ventilation blowers, run grounding cables, and mount humidity condensers. The work takes 11 days. Whitmore tests each system and trains the crew in operation and maintenance. The Thomas Jefferson sails for New York on the 3rd of June. Whitmore travels aboard to monitor the systems during loading and the return voyage. In New York, he watches as longshoremen pour 10,000 tons of flour into the holds. The ventilation blowers run continuously. Dust levels remain low. The humidity system keeps particles from becoming airborne. No clouds form. The Atlantic crossing takes 14 days. Whitmore inspects the holds daily. He measures dust concentration with a portable meter. The levels stay well below the explosive threshold. The grounding system prevents static buildup. The crew reports no unusual conditions. On the 21st of June, the Thomas Jefferson docks in Liverpool. The cargo is intact. No fires, no explosions. Whitmore submits his report to the Ministry of War Transport. He includes technical specifications, installation procedures, and cost estimates. The ministry approves immediate implementation across the grain carrier fleet. Whitmore receives authorization to requisition materials and coordinate retrofits at ports throughout Britain and North America. The scale of the operation is enormous. 340 Liberty ships carry grain on Atlantic routes. Each requires the full retrofit. Whitmore establishes installation teams at Liverpool, Glasgow, New York, and Baltimore. He writes detailed manuals for shipyard workers. He creates training programs for merchant crews. Every captain must understand dust management protocols. The retrofits begin in July 1943. Whitmore travels between ports to supervise quality control. He inspects completed installations and certifies each ship as safe for grain cargo. The work proceeds at a rate of 12 ships per week. By August, 80 vessels have the new systems. By September, 160. Whitmore also redesigns loading procedures. He orders grain elevators to install dust suppression equipment at loading chutes. He requires slower pour rates to minimize airborne particles. He mandates that ventilation systems run during the entire loading process. These changes add 2 hours to loading time, but reduce initial dust concentrations by 60%. Crew training is equally important. Whitmore writes a manual titled Dust Management for Merchant Seamen. The manual explains the physics of dust explosions in simple terms. It provides step-by-step procedures for system operation. It includes emergency protocols if dust levels rise unexpectedly. Whitmore requires every officer on grain carriers to complete a certification course. The results are immediate. In August 1943, no grain ships suffer explosions. In September, one vessel experiences a minor fire quickly extinguished by crew. In October, 0 incidents. The catastrophic explosion rate drops by 87%. Ships that would have burned now reach Britain safely. The impact extends beyond preventing explosions. The ventilation systems improve overall cargo preservation. Flour arrives in better condition. Less spoilage means more food for the British population. The Ministry of Food calculates that the systems save an additional 12,000 tons of grain per month through reduced waste. Whitmore continues to refine the systems based on operational experience. He adds redundant blowers after one ship loses ventilation due to electrical failure. He improves the humidity condensers to function more efficiently in tropical waters. He develops portable dust meters that crews can use for daily monitoring. Each modification is documented and distributed to the fleet. By December 1943, all grain carriers on Atlantic routes have the complete safety systems. The installation program expands to ships serving Mediterranean and Pacific routes. Whitmore trains additional technical officers to supervise installations and crew certification. The program becomes standard procedure for all merchant vessels carrying powdered or granular cargo. The British government does not publicize the explosion problem or Whitmore's solution. The information could aid enemy intelligence about convoy vulnerabilities. Whitmore's work remains classified throughout the war. He receives no public recognition. His name appears in no newspapers. After the war, maritime safety organizations adopt Whitmore's systems as international standards. The International Maritime Organization incorporates his ventilation and grounding specifications into cargo handling regulations. Modern bulk carriers use evolved versions of his designs. The principles remain unchanged. Control dust concentration, eliminate ignition sources, maintain safe atmospheric conditions. Whitmore returns to civilian life in 1946. He works as a consulting engineer for shipping companies. He never speaks publicly about his wartime service. The classified nature of his work prevents discussion. He dies in 1968 at age 73. His obituary mentions naval service, but provides no details. The full scope of his achievement emerges only when government archives are declassified in the 1990s. Historians discover his reports and technical drawings. They calculate that his systems prevented an estimated 63 ship losses between 1943 and 1945. At 8,000 tons of grain per ship, that represents over 500,000 tons of food, enough to feed 2 million people for 6 months. The Liberty ships Whitmore saved carried more than grain. They carried Britain's ability to continue fighting. Every ton of flour that reached Liverpool sustained factory workers building aircraft. Every shipment fed soldiers training for D-Day. The convoys that survived because of his work made invasion possible. Whitmore solved a problem that combined physics, engineering, and logistics under wartime pressure. He identified the cause of explosions through systematic investigation. He adapted industrial safety methods to maritime conditions. He implemented solutions across hundreds of ships while convoys sailed under constant threat. His work required technical knowledge, organizational skill, and the ability to train thousands of men in new procedures. The silent killer he confronted left no dramatic evidence, no torpedo tracks, no enemy aircraft. Just fine particles suspended in darkness, waiting for a spark. Whitmore made those spaces safe through forced air, grounded metal, and controlled humidity. His systems transformed volatile cargo holds into secure compartments. The ships reached port. The food reached Britain. The nation survived. Today, bulk carriers worldwide use descendants of Whitmore's ventilation and grounding systems. International maritime regulations mandate dust control in cargo operations. Training programs teach crews the principles Whitmore codified in 1943. The methods that saved convoys in the Atlantic now protect commercial shipping on every ocean. His engineering solution became invisible infrastructure, present in every hold carrying grain across water. The explosions stopped. The ships sailed. The work endured.